Right, so what's there to say? Okay, so I think we got I think we're basically fixed. I did find a ton of typos in the syllabus, so I think that's roughly fixed. I picked that around by noon yesterday. Um, and I think we finalized our homework zero. It just turned out to be what we did last year. No, so no changes in case you had already looked at it. Um, but right, as not just this class, we can do this again next class. But I'm happy to answer any questions you guys might have. Yeah. Oh, okay. Okay. Title. Okay. We need to fix title. Sorry. Okay. Besides the title of the class, which seems to be the highest order bit, um, what else? Any other questions? Yeah. Yeah. Is it always necessarily true that there is a linear time algorithm for? Oh, is it always true that you can verify at least as fast as solving? Um, well, to some extent, a deterministic algorithm that's actually proven correctly, if you just like looked at, like, imagine the computer's doing the steps and you know the algorithm's correct, and let's say you just wrote down the steps as you went along, right? And then afterwards you can just go through and say, oh, that's the right next step. You can read it and verify it. So that, for example, would give you like a certificate of a correct answer that's always as fast as the sequential algorithm. So I think, yeah, if you have an algorithm that's proven correctly, let me give a better answer actually and step back. Okay, so let's say, let's look at some problem where you have a good, efficient, correct algorithm, okay, and it gets the right answer and you know this for sure. And then someone gives you some solution and claims to say it's the right answer, right? And so your task is verifying, or, is this really a good answer or not? What would you do? So you have an algorithm that can find solutions and you want to verify. Yeah. Yeah, you can compare the two answers. So in most cases, I think that would fall under that. There are some weird situations, like when randomization is involved. There are a couple problems out there still, kind of famous conspicuous examples, where we have a very fast randomized algorithm that will work 99.9999% of the time, no matter the input. So it's still kind of worst case, and we'll do more of that at the very end of the semester. Um, but it's a problem for which our best algorithm is randomized. The best deterministic one is much slower. And in fact, even kind of double checking your answer, we don't have anything as fast as the randomized deterministically. So there's a few kind of interesting cases that shows up. Um, until very recently, one such problem was given a graph, which is we haven't discussed them yet, but points and edges. And you want to, if you remove some edges, you might be able to disconnect the graph, right? Like Facebook graph, you remove some friendships and you get a complete disconnect between two parts. So that's called a cut. And the problem is, how do you find a minimum cut in the graph? So you want to remove the fewest number of edges so that the graph is separated into two or more components. So for that, we had a nearly linear time, you know, number of edges times some logarithmic factors, randomized algorithm from computing the minimum cut since 1998 or something. And I think only last year we figured out how to do it deterministically in the same time. And the determinist algorithm is way more complicated. Um, but for a long time, we could actually compute minimum cut with very high probability, but some level you couldn't even double check that it was truly the right cut. You're guaranteed it's going to be right like almost 100% of the time, but to actually know for sure until recently. So there's related conjectures like, can any randomized algorithm be do randomized things like this, especially in the same time, right? Because it might be hard for you to believe at your vantage point, but sometimes randomization will let you kind of get at certain things, and there's some tricks you can do, and you can get much simpler algorithms if you use randomization. And the deterministic algorithms, which is probably what you're more comfortable with at this stage, is actually lagging behind. but there's sort of some sense that like, oh, if you can do something randomized in such and such a time, eventually we'll figure out how to do it deterministically in such and such a time as well. But it takes a long time, and sometimes you have to do weird things to try to catch up. It's more of a theoretical question to see if there's always a gap, because it's really asking, is there an essential role to randomization in some deeper sense? Okay, so that was okay. Yeah, a great question, and maybe you didn't want that long of an answer. Other questions, also particularly about logistics. Probably we'll just like learn the rules as we accidentally break them along the way. That's usually what happens. So it won't be that big a deal. All right. Um, good. But I'll put up this slide again next time in case you actually looked at the syllabus in the meantime and had some questions. Okay. Um, good. So I guess we just kind of covered this to some extent. So last time we did some searching and sorting, pretty standard stuff. Introduced big O notation. You'd probably seen it before. We even did some lower bounds, which hopefully was more new. Um, and the big thing was it was sort of our first recursive algorithm, merge sort. It was particular emphasis in this class on writing a good recursive spec. That's really the inductive hypothesis of your proof. That's also kind of how you design recursive algorithms. When you declare what your algorithm is going to do, that gives you kind of a reliable subroutine when you're implementing itself with itself, and So, if you think about it in the wrong way, it can be confusing, but you think about it in the right way, it's not a big deal. Just declare what the algorithm is supposed to do, and now you have something to work with, right? And this is very powerful because it's a natural way to take big problems and reliably break them down into smaller problems. Yeah, so that's very natural. Okay, so this might be taking even a step backwards compared to last time, so I apologize. But I have learned that it is good to make sure we're all on the same page when it comes to induction. So we'll do a lecture on induction. I'll try to make it still entertaining. I found at least a new proof of a new theorem that I only learned recently. So hopefully that will still be fun. Okay, so let's go over induction. Presumably you guys have been exposed to induction quite a bit. So maybe we can go faster if appropriate. So, okay, here's the usual silly thing. Okay, let's say you're trying to climb stairs. You're trying to make a robot that climbs stairs or something, right? How would you explain climbing stairs to somebody, especially for a very long staircase? Not a trick question. Yeah, yeah. So I think that's a good answer. Here's something I wrote, I guess. Uh, Take it one step at a time. This is what you said, right? Put one step up, one step another. Put a little effort to make it look nicer. But I think you get the general idea. But I think the most important part of this instruction that I put up is just the very first sentence, right? So in the very first sentence, you already recognize that every step as you go up a staircase is going to be identical, right? You're not going to be like, well, the first stair you should do this, second stair you should do this, third stair you should do this, fourth stair. That's insane, right? No, they're the same, and you just have to create the pattern, and it repeats itself, and you're totally confident that it'll get you to the end. Yeah. But again, I think that's last part then is the important leap. This claim that you'll eventually get to the top if you just treat each step kind of one at a time, right? And this is where induction is going to do all the work for us. Okay, so presumably you've seen something like this before. This is not too deep, right? But if you're trying to instruct a robot how to climb a staircase, so it's one stair, that's immediate. In fact, 0 stairs would have been easier, right? Okay, so you can do one stair. And in the general case, you're looking at a staircase is more than one stair, right? And what's interesting about the claim is that you want to do any number of stairs, right? Of course, stairs are kind of simple. Also, it's not really very rigorous. But the interesting part is you want to do something that works for all n, right? And so a proof, and I put proof in quotations because it's not a very rigorous thing we're looking at, right? Let's assume that the instructions work for one step, whatever that is, right? And once you take one step, n minus 1 steps remain, right? And then we're going to assume by induction, if we're trying to prove it works for n steps, that it works for any staircase with less than n steps. In particular, it works for n minus 1. Right? If you take one step and now you're on the first step, what remains is a staircase of n minus 1 steps, and you're already promised these instructions work, and that's it, right? So by induction on n. Okay, no big deal. I think you've all seen this before. Okay, all right, so let's start having more fun with games. First of all, has everyone done this puzzle before? Virtually everyone? Looks like it. Okay, so then you should know the answer. Okay, so you have then you know the rules of the game. You have n rings. They're the biggest ones on the bottom, and they're in decreasing order up to the top. And your goal is to move all the rings from A to B, but you have to maintain this order. So you can't put a bigger ring on a smaller ring, right? Okay. And so the question is how do you do this? How do you do this? Yeah. Okay, I think you have kind of okay. I generally agree with the sentiment and the direction and all this. Uh, but it was quite a long answer, and I kind of lost track of what you're saying, but it seemed kind of correct. What would be like a very easy answer? Yeah. Yeah, okay, so here's an algorithm. You're going to move n minus 1 rings to C, okay? You're going to move one ring to B, and then you're going to move n minus 1 rings onto B, okay? This is much easier, right? So what do most people do? They see this puzzle, and they start moving one ring at a time, and they start imagining one ring and things like this, right? But even for like 5 rings, it's going to take you a really long time to like map everything out. Right? You might even be wondering, should I put that first ring on B or something because I'm doing something weird, right? Maybe if it's odd or even, you're not even sure, right? Uh, but I kind of cheated. I'm just going to move n minus 1 rings, right? And if the question is how do you move n rings and you have in your pocket how to move n minus 1 rings, it's very easy, right? There's nothing to this puzzle, right? But that's exactly what I'm suggesting you can do now, right? So it's a very easy puzzle if you use induction. If you don't use induction, you know, right? I mean, I got lost and you only got up to like 3 rings. So, okay. So to do this properly, then I'm going to force you guys to do this as a teacher. Um, we need to first just define a recursive spec, right? So I want to define kind of what I'm doing so that it's kind of justified when I make these recursive calls. So we just need to give it a name and some parameters and then a sentence. So who wants to give a name? Okay, I'll give a name. All right, TOH for Towers of Hanoi. Yeah, simple enough. Okay, now we need some parameters. What are we trying to do? Okay, number of rings, I'll write N. There's 3 towers. Yeah. Yeah, so we can do something like, right. So I think maybe I'll let you then specify the sentence because I think you have it in mind. Yeah, so maybe move n sorted rings from A to B, you know, in order, playing with the rules, all these things. Okay. But, that's the subroutine we're trying to implement. You're given n rings on post A. Maybe I should have written given n rings on post A in sorted order. I want to move all of them to B, again, in sorted order, while maintaining the order at all times. Yeah? Okay, good. So that would be simple enough spec. Yeah? So, okay, I guess I worded it slightly differently, but you get the same idea. Okay. So the next thing then, now that we have some clarity about what we're trying to implement, is we just need to implement it. Yeah? So, who wants to implement it? Yeah. Right. So that means that I want to just permute those two arguments because I'm not going to C instead of B. Yeah. Okay. Yeah. Yeah. I will wait for you guys to answer no matter how. Oops, got back. Obvious you think it is. Okay. All right. So that was sort of the algorithm we described, right? We're going to recursively move n minus 1 from A to C, move them out of the way, move one over, and then move them back. Yeah, simple enough. Small bug in the code. Yeah, if n equals 0, return. Maybe slightly more slick is just if n is greater than 0, then do something. Otherwise, they'll do nothing. Okay, simple enough, right? But it's just 3 lines or maybe 4 lines of code. Okay. But I'm 100% sure it's correct because of the recursive spec in particular. Once you make it really clear what you're trying to implement, then it's really clear what the subroutine provides for you. Right? It's very easy. Okay, good. Same thing there. All right, so I mean, just for maybe sake of practice, like what would sort of a proof of correctness look like? Yeah, yeah, induction on, and in particular. Yeah, so I'm just going to take the recursive spec, just treat that exactly as an inductive hypothesis and say, okay, this code is going to implement exactly what it says it will for every value of n. Then we're done, right? Okay, so where do we start? In the base case, you, yeah, you could make the base case n equals 1 or 2, or we'll start with the base case. Who wants to pick a base case? What's the easiest base case? Yeah, you could do easier, I think. Yeah, okay. Base case n equals 0, there's nothing to do. Yeah, the algorithm's clearly correct. There's no post to move. The algorithm doesn't do anything. Okay. It's an interesting case. There's n greater than 0, right? And you want to prove it's correct. Uh, but what, you're just going to leverage the fact that your recursive calls are correct by induction, on n. Yeah. And then once you have that, then it's very easy to say, okay, well, by induction, this is going to correctly move the top n minus 1 rings from A to C, without breaking any rules. Yeah. And then I can move one from A to B because I know there's nothing on B and there's nothing on top of it in A. And then by induction, it's going to correctly move n minus 1 back from C to B. Yeah, so it's not hard once you have the inductive hypothesis to prove that it's correct for n. I'm guessing you have done something like this before. Yeah. No, there's no conflict of interest. You're supposed to use induction to prove. So I think induction is sort of like a principle that we assume is correct. Yeah. I think you're thinking too hard about it. So induction and recursion are very similar, more or less the same. Yeah, at least correct recursion and induction. Right? And the thing we're trying to prove is that the algorithm, the subroutine implements the spec for each value of n. So inductive hypothesis is that the algorithm will implement it for the value n minus 1 correctly. And so it does go down a level, so it's okay. Yeah, yeah. So if you didn't have step C, n equals 0 will be okay, but any general case you get stuck, right? Uh, so in particular, this step here will do n minus 1 correctly, and you want to prove n is correct, right? But let's say that even your algorithm, you just assume it works for 9 rings, and you're trying to prove 10, right? And you say, oh, I moved 9 rings over from A to C, I moved 1 ring over from A to B, and I'm just done. But you didn't finish moving the 9 rings over, so that would break. It is true that by coincidence it'll be correct for n equals 1. But for n equals 2, you're immediately going to get in trouble. You'll move 1 ring over from A to C correctly. Then you'll move 1 ring over from A to B correctly. And if you just terminate, someone's going to be like, well, you left the ring on post C. No, no, the recursive calls to n minus 1 rings is correct. So say the case n equals 2. So you are moving 1 ring over correctly. But you're trying to say that if I can move 1 ring, then I can show you that I can move 2. But if your algorithm is missing step C, even though you can move 1 ring correctly, you wouldn't be able to move 2 rings correctly. So induction is only for smaller inputs that it's correct in particular. So I didn't write out the full thing. This is just like, yeah, yeah. Otherwise, I would write, okay, yeah, by induction, this moves n minus 1 things over correctly. And then I move 1 ring over. And that's okay because the posts are cleared and things like that. I didn't want to write it all because I didn't think that would be very fun. And then by induction, I can move n minus 1 rings back from here to here and then say, okay, now they're in order because of this and that. Yeah, I'm a little lazy. Yeah. Are there cases where induction breaks by the base case? Yeah, so like, mistakes that might come up, right? Suppose like for some reason your proof is like, oh, I go from n to n divided by 2, right? And your base case was like 0 or something, right? And then you start getting to fractions closer and closer and closer to 0, but you don't necessarily get to 0, right? So you can't just willy-nilly. But in general, if you're always able to kind of order the cases in some total ordering, in this case, it's very simple. 1 would precede 2, would precede 3, would precede 4. Um, so that you could have simulated, I did 1, then I did 2, then I did 3, then I did 4 based on 3. So if you always have an ordering like that, you're fine. And in most cases, it'll be pretty clear. And I think if you're just on your toes, you'll be able to avoid the unusual cases too. Yeah. No, 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 on the homework you'll be a little bit more formal, but then there will be some problems I think coming up actually. So I had some choice between giving you one problem and you write a two-page proof of induction that's not very interesting, or I give you five problems and I say you only have to write the recursive spec for these and I'll treat it as an inductive proof because I would rather get you exposed to lots of problems. So that first homework is a little bit more focusing on problem solving, but I still want you to write the recursive spec. And the way I'll evaluate it is I'll say, if I wrote a proof by induction, would this recursive spec be strong enough? Yeah, but spare you actually writing it because otherwise it just goes on and on and on. And I would rather get you to solve a lot of problems quickly. But there'll be some other homeworks down the line where I'll be a little more, yeah. So there's some trade-off. I agree. And we try to be mindful of, yeah. Okay, is that okay? All right. Sorry. You want to calculate runtime? We can calculate runtime. Um, sure. Let's do that now. So you want to calculate the running time. So how should we model the running time? Okay, that's the number of moves. Yeah. And what would this become? So yes. Yeah. So we don't have to fully do a tree like we did last time. This one you can kind of eyeball and unroll it if you wanted to. So tn minus 1s are going to get replaced by 2 tn minus 2. So you get 4 2 tn minus 2 plus 2, so on. In general, you're going to get like 2 to the I, t to the either n minus I or n minus I minus 1. I think n minus 1. I plus 1 or something, right? Oh, no, I'm doing that wrong. I'm doing that wrong. Yeah, yeah, yeah. Okay. Um, all right, this becomes plus 3 and so forth. And you're going to get something like 2 to the n minus 1 or something. I forget. Yeah. But you're going to get something exponential because you're just doubling every time. Okay. Good. So I want to ask you guys a slightly more uh, rigorous version of the question. Okay. So the usual puzzle is how do you get from A to B? And is it possible? And things like this. And it's possible by induction. Okay. But now I want to I'm going to ask for more. I'm going to ask you to get from A to B was the minimum number of ring moves. I don't know if you guys have done this before, but you have done this before. Okay, yeah, so how would you do it? Yeah, so how would I justify it then? How would I get that down on paper? Your ideas are good. Okay, so what would I do in particular? So you definitely have the right ideas, but the question is how do we really put our finger on it, right? How do I make this sharp? Yeah. Okay. Sure. So here's one. How would I change this? That's the one from before. Yeah, that's it. We just changed the inductive hypothesis, right? And say I'm going to try to move all the rings from A to B with a minimum number of moves. And nothing else changes. The algorithm doesn't change. I know I have to move n minus 1 rings out of the way from A to C. I might as well do it with the minimum number. I have to do it with the minimum number of moves. Yeah. And that's it, right? So all you have to do is strengthen the inductive hypothesis and you get what you're looking for. We can redo the proof, but it's the exact same thing, right? You know you have to move n minus 1 rings out of the way from A to C. By induction, that's the best possible way to do it. Yeah, that's the minimum number of moves. So you're not wasting anything. You know you have to move a ring from A to B. You have to pay one. And then you know you're going to have to move the rings back from C to B after you've moved that ring onto B. And that's by induction the minimum number of ways to do it. Yeah, so those are three steps you have to do. And the two big steps, the n minus one ring steps, by induction you're already doing it optimally. Okay, so we just redo that conversation before with an extra clause added. Nothing changes. Yeah, so that's supposed to dramatize the power of the recursive spec. Okay, no big deal. Questions? All right. So, all right. The next topic I had up has another example of an inductive algorithm. Was going to be computing the greatest common divisor. Do you guys already do this too? Okay, I saw like one or two notes, but we'll do it quickly then. Okay, what's the greatest common denominator of these two numbers? It's guessable. No, that's no fun. It's bigger. 15 maybe? I mean, if you put maybe, then what can I say? Yeah, you look at your phone. 390. Okay. All right. So we'll do this then quickly. So we're going to make an algorithm, I guess, due to Euclid. It's going to be based on a pretty simple idea, right? I want to get the greatest common divisor of x and y, so some number that divides both of them as big as possible. And let's say that x is the bigger of the two. Okay. If some number divides x and y, right, then it's also going to divide x minus y. Yeah, we're just going to try to leverage this and try to make an algorithm. Okay, so, right, so okay, we'll do this quickly because I think you guys find this boring. What would be a recursive spec for the greatest common divisor? You want some algorithm, right? Might write GCD xy, maybe given integers x squared and equal to y, then what? We're not doing the algorithm yet, we're just defining the what input output. Return the GCD of xy. Okay. In many cases, the recursive spec may not be very interesting. Right? You should be restating what you're kind of asked to do. Okay. So fine, no big deal. I guess I was a little bit more careful. For the proof, it'll be convenient to assume that x is bigger than 0 because 0, 0, then you have to write some extra case. Okay. And I'm going to assume x is greater than or equal to y, so I don't have to flip it into our algorithm. Okay. So, all right, let's implement this. How do you want to implement? Yeah. All right, if y is 0, return x. Yeah. Okay. I'll just write this since you put it. I was lazy in my version. I just skipped this line. But um, uh, okay, so otherwise, you want to return the GCD of, okay, I'm going to be a little bit pedantic here because I was insisting that x is the bigger of the two and that y is the smaller. And I'll return that. Okay, so I just wanted to make sure that the first parameter is the bigger of the two numbers and the second one is the smaller. Yeah, otherwise the code would get messier up above. It's in the, yeah, Okay, simple enough. Okay, so that's the same code except that x prime, y prime is inlined. Yeah. Hmm. Oh, this I get backwards. It should be y. Okay, good. I make a lot of mistakes like that, so it's good to catch them. All right. So what comes next? I think we just need to prove this thing. How can we prove it's correct? Yeah. Hmm. Okay, so the initial suggestion was like, well, if y divides x, why not just return y right away? That would probably be also practical. Yeah. And so it wasn't trivial. I would say if we can prove this thing is correct, that would sort of be an answer to your question, right? Um, yeah, so I think from my perspective, I would just try and write the fewest lines of code to be the easiest on your eyes, and that was it. But there's certainly nothing wrong with, shortcutting an easy answer when it appears. Yeah. Yeah, yeah. Well, in that particular case, it will work, yes. But in general, if I prove this thing is correct, then we'll be happy. Yeah, yeah. And I think, we're only getting worst case bounds, so we can't really assume much optimistically anyway as far as bounding these things. Okay, but how would I prove this? Probably by induction, given that's the lecture, but by induction on what? Okay, yeah, so there are some base cases. Then you have to have x is equal to 1 and y equals 0, so the answer is 0. Okay, it's fine. Something weird. All right, but we can keep doing the proof. Do you want to do a general case? We'll see what happens. Let me see what I wrote as the simplest version of this proof. Oh, okay, yeah. Sorry. You divide. So the GCD of some number and 0 is some number by definition. 5, 0 is 5. Okay. So, okay, let's go to a general case. Suppose x plus y is bigger than 1. Yeah? Okay, and we just basically have to trace through our algorithm, right? So what should I write? Yeah, being a little bit informal as always. Let's see if we can finish this. You guys, you're very close actually. You just need to fill in this last part. So suppose y is not 0. So y is 0, that's easy because x is the answer, and the algorithm handles that correctly. Yeah, so let's just make it proof. I think you guys have the right idea. Yeah, so recursive calls to x minus y and y in some order. It could be flipped. Okay, and right. So we add together x minus y and y, you get x, and that's less than x plus y insofar as y is at least 0. Okay, so your sum is smaller. So your recursive call to x minus y and y in some order will be correct. And we just pointed out the GCD of the x minus y and y is going to be the GCD of x and y. Yeah. I guess the biggest thing is that it works. And anything else that works will be just fine. But you want to find some kind of meaningful progress. And it might match your intuition, right? You're kind of thinking, oh, if I subtract y from x and I submit them, then something is going down. And you fumble around, oh, it's just x going down, it's just y going down. You did just x or y alone. It gets a little confusing because you did the max and min. The sum goes down. If you have 10 and 10, quite possibly, but I would write it out to double check. Yeah? And you could have also tweaked the algorithm and changed the proof accordingly. I would be a little bit careful about the first argument because 10 and 10 will give you 10 and 0, which in your mind is not a big deal, but technically the first argument did not go down. So you have to do something clumsy to get around this. Maybe adjust the algorithm or something, or you can just fall back on x plus y. But different algorithm, slightly different tweak, if I hadn't swapped or something. Sure. We just want something that works, right? And anything is fine. But actually, just so this will come up in a moment. There'll be a little more nuance to it. But let's go over to running time. How long does this algorithm take? Okay, so why? Yeah, so that would be the worst thing, but let me try to articulate slightly differently. So as long as y is bigger than 0, each time x plus y will go down by 1, right? So, you know, at most x plus y, whatever your initial values of x and y are. Okay. My next question is that a good linear time algorithm? This linear time. Okay, why is it? Yeah, and so what's the size of x and y? Yeah, so you only really need log x bits to represent x, log y bits to represent y. So our algorithm is actually exponential on the input side. Okay, so it's actually a pretty bad algorithm. I can give you a huge numbers with a very small amount of memory, and your algorithm will never terminate. Okay, so the question is how can we do better? Yeah? Sure, that's coming up. Okay, well okay, so the bad case then, I think you all figured this out, is something like, say, 101 and 2. Yeah, and your algorithm is going to go 99, 97, all the way down, and this will always be 2. Okay. All right, so let's do exactly as suggested. This will be a little bit more aggressive. So let's say x is bigger than y again. Let r equal to x mod y. Okay. So it's not hard to see, like if you kind of worked out the part in purple, that q can divide x and y if and only if q divides y and r. Yeah. Okay. Since r is equal to x minus ky, and x is equal to ky plus r for some value of k. All right, so that is then maybe a better algorithm, right? It's more aggressive. Okay. Here I don't have to do any weird switching because I know x mod y will be smaller than y. All right, so let's prove this thing works by induction. I mean, you guys probably all believe it works, but let's just try to figure out how to get that down on paper. Yeah? And part of the tough part is figuring out the right thing to do induction on. Any ideas? Or, yeah. Yeah, well, there's nothing behind that box. Yeah, so we can try to do proof by induction on y, right? Because actually, in this case, we can see y is always going down because that r is going to be smaller than y. Okay, good. So what's the base case? Y is equal to 0, then the GCD is x and it's correct, so I won't write that out. Okay, and in the general case is when y is bigger than 0, because so oh, I'm being a little bit confusing between what's the algorithm and what's the math. Uh, okay, so we know that GCD YR is correct. It returns GCD of y and r because r is smaller. Yeah, we're doing induction on this. And then mathematically, we know that the greatest common divisor of x and y is the greatest common divisor of y and r. Okay, this one's actually easier in some ways to prove. Slightly. The other one wasn't that hard. Okay. Uh, good. So maybe more interesting then is the running time. So this feels more aggressive. It should do about no worse. But let's see how good the running time can be and how we can try to justify it. Yeah. Okay, how are you going to get rid of one bit? All right, so I think we just want to figure out how to articulate this cleanly, right? Because I can't say suppose you have 9 bits, for sure it'll be 0 or something, right? Like that. Because I want to make a fully general. So for example, take your example of 9 and 8. And I think if x was like 17, then you'll get 8. You'll get 8 and 9. But both of those will require 4 bits. Yeah, so we just have to figure out how to get this down nice and clean. Uh, any other suggestions? Yeah. Oh, oh, is that always true? Okay, here's what I said. I said it takes 2 iterations to decrease y by half. Okay, which actually that version might be more slick, but we'd have to be a little more careful. So in one case, if r is at most y by 2, then we're happy. That already decreased y by half, right? Now, suppose r is at least y by 2. And the next call is going to do some GCD to y and r, right? Um, but y mod r, since r is at least y by 2, should be at most y by 2. Okay, so in 2 iterations, I should be able to decrease y in half. Now the rows of x and y may switch, so every 2 iterations is going to get rid of 1 bit from one of the 2 sides. Okay, so you get log s plus log y. Okay, so that takes a little more care. There might be more slick ways to do it. This is just whatever I came up with, sitting on an airplane or something, right? Um, but yeah, you have to be a little more careful. Okay, questions? This is your linear running time. Okay, all right, so this is the new part, hopefully for you all. I don't really know if it's going to go very well, but we'll see. Okay. But any questions about the previous before we venture into the unknown? Yeah. Yeah. So we always model running times as a function of the input size. Linear is particularly nice because it just some constant times n. So the word linear comes up a lot. But in general, it could be some weird function. And usually linear is best you can do, so you're pretty happy. Most problems require you to at least look at the input. Um, and yeah, we haven't really gone into super interesting algorithms yet. Last time we had n log n running time for sorting. That's sometimes called nearly linear when you have these extra logarithmic factors, because the logarithms are quite small compared to n. Um, we'll have n squared algorithms that's sometimes called quadratic. You don't have to know all these English names for all these numbers. It's not that important. It's only when I discuss it makes it easier. Um, yeah. I think the answer must be yes to your question. And in the before the catch was just that bits can be represented, numbers can be represented in logarithmic size of their value. So x plus y was actually an exponential function of the input size. And that's all that was trying to say. I'm sure we can think of other numerical algorithms with only one input number. And you can have a log x algorithm or an x kind of algorithm. If you want to compute square root x or something, you can enumerate everything and keep squaring and see if you find a number. That'll get you something like x running time or something, right? Or square root x running time. But then if you do something more clever, you can get something more like log x. But that'll be one input kind of thing. Yeah. Yeah. There'll only be like one or two getches that come up later. But yeah, so we should be mindful of the actual input size. And at the end of the day, what we really want is to model the running time as a function of the input size. Yeah. I think this particular point won't come up for a while, and yeah. For example, I'll have lots of algorithms where I'm adding up two numbers. Technically, that should take a logarithmic time to add up log x bits with log y bits, and we just treat that as a constant because we're friends. Okay. Yeah, and it's fine. So let's try this. So this is a problem that's also going to come up again later. It's a classic problem in optimization computer science. Okay, so this is a graph. I think you've all been exposed to graphs, but graphs consist of these points, vertices, and these lines between them, edges. And this is a bipartite graph. I can divide the vertices in half. All the edges go from left to right. Okay, so we're going to focus specifically on bipartite graphs for the next segment. So a matching, okay, the goal is to try to take as many edges as possible so the endpoints don't meet. Okay, sometimes this is like, yeah, is this right? So your goal is to find the maximum number of edges so that the endpoints are all different. Sometimes this is also called or just shows up in an assignment problem in optimization where you have some goods and they're being allocated to factories and there's one good and each factory can only take one good or something and you're trying to match them up, right? I think what they were trying to assign people to boats in World War II. And they actually do this kind of thing, early use of computers. Okay, so you're trying to find maximum number of edges that are disjoint. What's the best you've come up with for this instance? Hmm. So you're trying to take as many blue lines as possible so that the endpoints are all different. Did you get six? So they can't touch each other at all. So if they meet at one endpoint, that's bad. Yeah, they should be completely disjoint from each other, whatever you take. Yeah, what you get? Five? Okay, so I'm going to point at some edges and you tell me whether I should take it. All right, so I'll start at the top. Should I take this first edge? Okay. So that means that I cannot take this edge because I've already used up the left endpoint. And I can't use that edge because I've always used up the right endpoint. I also can't take that edge or that edge. Okay. So our next choice then would be, I guess, this edge. Should I take this edge? Yeah, okay, we'll take it. And this will cancel out a few more. I think our next choice, this one's already canceled out from up above. So is this one. So our next choice is here. Should I take it? Okay. All right. Can't take that one. Should I take this one? Can't take that one. Can't take that one. Can't take that one. Can't take that one. Should I take this one? Oh, okay. And then we're done. Okay, so that's 5 edges in a matching. All the endpoints are disjoint. Can anyone do better than 5? It's hard to tell. You're just pretty sure you can't. You have 2 that only. Ah, okay, good. So here you can actually try to prove. I guess if you looked at these 3 vertices, you'll never be able to attach more than 2 edges to them. Okay, that's actually pretty clever. No one's pointed that out before. Okay, good. All right, that's similar to one I had. I guess I cross edges for the sake of variety. Okay, and then let me give you another problem that's going to be closely related, but sort of opposite. So again, bipartite graph, same setup as before. This is called the vertex cover problem. So now my goal is to choose vertices so that every edge I'm taking at least one of the 2 endpoints. So I want to take as few vertices as possible to make sure I cover all the edges. Covering means I've taken at least one endpoint. I'll torture you guys again, see if we can. Okay. This. Does this cover all the edges? This one? Oh, this? And then removing. Can anyone do better than 5? Get rid of the last one on the left? Okay. We have some edges. Oh, the bottom edge is uncovered. Now you have to figure out how to fix it. Should I put it back? I'll briefly put it back. Can anyone do better than 5? Yeah, well, I mean, have to is a strong word. I could have these 3 instead, but it'd be a little inefficient. Certainly, those 2 feel very appealing. Can you do better than 5? It's the same graph as before. Okay, good. So, right, so this, yeah, okay, so for what it's worth, both of those problems actually, you had a very clever approach for the matching, but in general, even if you have the right solution, or you think you have the right solution, it's a little tricky to know if you can do better, right? Okay, so we're going to address this as pointed out. So these are called dual problems, okay, in the following sense. In the first problem, you think of it as like packing a suitcase. I'm trying to take as many edges as possible, but there's these constraints on the endpoints on the vertices. Each vertex, I can only take one edge incident to it. I'm packing edges into vertices, most one edge per vertex. Yeah? On the flip side, I'm covering the edges with vertices. It's the same kind of incidence structure. So I have all these edges. I'm trying to take as few vertices as possible. I need to take at least one vertex per edge. Okay. So A is being packed into B. B is covering A. And sort of the packing covering incidence is the exact same. It's the same, you know, A packs B if and only if B packs A. Okay. So these are called dual problems. It's only one example of many. And in fact, we won't see this again until the latter half of the class. But a lot of optimization problems have this setup. There's something you want. There's also a dual problem, which may be of interest. Okay, good. So this is one way, by coincidence, the best matching you came up with equal the best vertex cover you came up with, right? And we're going to see to what extent this is a coincidence. Okay, so whenever we have really this kind of setup, but we can just focus on matchings and vertex covers, okay? The claim is that if I give you any matching and any vertex cover, here's some set M and some set C, the size of the matching is at most the size of the vertex cover. So you guys came up with 5 and 5, but the vertex cover had to be bigger than the matching, right? 5 and 5 is okay. In fact, that would certify them to be both optimal because you can't do better. Okay, so you actually came up with dual certificates. Okay, but how do I prove this? Why is this true? Is this surprising? Okay, how would you do that? Yeah, I'm just pushing us to try to figure out how to really articulate. Yeah. Yeah, so here's maybe a slightly verbose way to do it. I can write the number of edges in a matching as 1 per edge, right? Not a big deal. And then like you said, we know the vertex cover has at least one endpoint from each edge, right? So for each of these edges, this will be dominated by, I'll write C and E. How many vertices in my vertex cover are kind of intersecting with E, if I think of E as a set of 2 vertices, okay? And so this is just because C is a vertex cover, okay? Now, eventually I want to show this is at most the size of C, okay? So what do I write next? Yeah, so why should the sum of intersections be less? You're particularly worried about like overlapping and double counting and things like this, right? So the suggestion is that maybe you're not going to double count, but why? So the edges have disjoint endpoints. So whatever overlap it has as the vertex cover is going to be different vertices. Okay, so because M is a matching, M is disjoint, then you're going to get this like, you can take the union of each of these sets. You're actually never double counting. Okay, and then now the union, they're all subsets of C's that are going to be contained in C. Okay, yeah. Yeah. So if I think of C as 2 endpoints as a set, and then C as another set of a bunch of endpoints, of a bunch of vertices, and not just, yeah. So whatever set vertices are in both. I'll just treat them both as sets of vertices. And so yeah, it's a little bit unfriendly, but also you don't want to watch me write all day either, so there's some trade-off. Okay, good. So it's not a very complicated, it's kind of straightforward, right? And it's just dealing with like the incident structure that A packs into B and B covers A, right? And the A's are disjoint or something. You know, very little structure went into this theorem. Okay, so that's called weak duality. And actually now you actually know that both of your answers of 5 and 5 are correct because there's always this lower bound. You couldn't have done better. Okay. But now we're going to, oh geez, we're running out of time. Are you leaping ahead? Have you, oh, well, can you hold the thought? Because I just have 5 minutes left and I want to try to, sorry to be, okay. So I want to at least present the theorem and see how much of the proof we can do. Okay. So in fact, these quantities will always be equal. And you'll see a different proof of this, more algorithmic at the end, but I'm going to present a proof by induction, right? But this is a bit miraculous. I wish I could give more time to kind of let it soak in. But the claim is that the maximum size of a matching of bipartite graph is always going to be equal to the minimum size of a vertex cover. So how are we going to do this? I'm going to be a little bit expeditious because I'm sure you'd rather get out of here than have me make this very rhetorical. Okay, so we're going to try to prove this by some kind of size of G. Here, I'll just add up the number of vertices and edges, whatever that is. So that means that I can always take away a vertex and I have a smaller graph and I can use induction. Okay. So the simplest base case is just 0. It's an empty graph, matching of size 0, vertex cover size 0. Yeah, I'm using size of G to denote the number of vertices plus number of edges in G. I put it really small here so that you can't see it. Huh? Because I'm even lazier. Yeah. Zero empty graph is also bipartite. Okay. So in a general case, you're going to have a bigger graph. You're going to assume it holds for all smaller graphs, measured by number of vertices plus number of edges. Okay. This is going to be a little bit sketchy. Okay. So let's say that you have a vertex cover of size k, and I'm going to use S to denote like the vertices on the left, T to denote the vertices on the right. Okay. My goal is to put together a matching of size k. Okay. And we're going to break it down into two cases. I feel like it's not as fun when it's rushed, but it's okay. Okay, and they're a little subtle. One case is that there's some minimum vertex cover where both S and T are non-empty. Okay. The second case is where every minimum vertex cover has either the left side non-empty or the left side empty or the right side empty. Okay. All right, so we'll do the first case first. This will be a little bit more of a mathy proof than what we had done in the earlier parts of the class. Okay. So what we're going to do here is first I'm going to kind of look at, say, this graph. I've broken it up into S and T. Okay. And I'm going to look at a graph where I first sort of like remove all the edges incident to T. Okay. So what I'm going to do is I'm going to remove T, and I'm going to remove all the edges incident to this. That didn't work out like I'd hoped. Okay. And I'm going to call this GS, G sub S. Okay. So this is a subgraph. And okay, good. So we know that since T is non-empty, this graph is going to be smaller. Okay, so now one thing I want to point out is that a vertex cover in this graph, like maybe these two and this, okay, it's not an optimal one, will also give you a vertex cover in this graph, because in particular, it will cover all the vertices that are covered by S and aren't covered by T. Okay, so if there was a better vertex cover on the S side in this G sub S graph, then I would be able to replace it up above. Okay, but that means that S must be optimal for this subgraph. If it wasn't optimal, I'd be able to improve the original graph. And that means I'm guaranteed some matching of size equal to S in this smaller graph by induction on the sides of the graph. Okay, so I look at the part of the graph that's not covered by T, argue that S must be optimal in this subgraph, otherwise a better one I could lift to the original instance. And in the smaller graph, I'll get two edges, in this case, because S was size 2. And those edges will also be disjoint from T, because that's how. Okay. And then we can do the same thing on the T side. Okay, we do something like this. I erase everything that's incident to S. Why doesn't that work like I hoped? Okay, anyway, I erase everything incident to S. T must be optimal within this subgraph. In this picture, it has size 3. So you're guaranteed a matching of size 3. And those edges are all independent from S as well. Yeah, so now you can put them together and you get, those two edges, those two together will give you a matching in the original graph. Some of them were of size S, some of them were of size T, so together you get size S plus T. Okay, so there we did induction on a smaller graph, strictly fewer edges, strictly fewer vertices. Okay, the remaining case, I guess this is going already 2 minutes over, so I'll do very quickly. So in the remaining case, every minimum vertex cover has everything on one side or the other, which I'm hoping is the case here. It looks like that's the case. All right. So now the proof says, okay, I'm going to pick any edge and I'm going to delete it, or imagine deleting it. So I'll make it dash like that. I'll make it a different color or something. That was an edge in the original graph. Okay. And I'm going to call this endpoint U and this endpoint V. Okay. Now, for any vertex cover in this subgraph, the vertex cover, it's not a very good one. Okay, so this would be, I think, a vertex cover in this graph where I remove this one particular edge. I know that green plus V would be a vertex cover in the original graph, and also green in this picture plus U would also be a vertex cover in the original graph, because I'm only missing one edge and I'm adding one of those back in. Okay. Now, if green happened to be all on the left side, okay, then green plus U will give me a vertex cover with some vertices on both sides. Okay. So let me say, imagine this isn't actually a vertex cover, but suppose this was some vertex cover with only vertices on the left. Then if I added U, the left-hand vertex of this missing edge, back in, then we would be covering the missing edge, right? And you get a vertex cover the original graph. It's not quite accurate in this picture. But we know by assumption that all minimum vertex covers are all on one side or the other, right? So that means green plus U is strictly bigger than the minimum vertex size. Okay? So in this way, you can argue that in this graph that I'll call G prime has a vertex cover of minimum vertex cover of size K. Okay. So if the vertex cover size went down by 1, then you would be able to add back in. You get a contradiction by adding a vertex on the opposite size. Okay. So in the smaller graph, you have a vertex cover of size K again. By induction on the size of the graph, there's a matching of size K. And of course, that's a matching in the original graph because all you did was delete an edge. Okay. I'm going a little quick, but I think you're eager to get out of here. So that's it. So that would be a proof by induction, sort of removing either one edge in one case or splitting the graph into two parts to get smaller graphs that the maximum bipartite matching is equal to the minimum vertex cover. Okay, I'll end it there. I wanted to say before closing.